right, let's continue. Let's look at this picture here. Now, when I get back, I'll do some demonstrations for you. But if you put water upside down in a bucket of water, it doesn't go down. Now, it seems to be overcoming the force of gravity. If you look at this picture here, let's get it on arrow. If you look at this picture here, the mercury should be pulled down by gravity and go down. Liquid seeks its own level, water seeks its own level, but it doesn't go down. So why not? And something's holding it up. And there is a maximum height that can be held up, and that is measured by atmospheric pressure. It's almost like a seesaw of atmospheric pressure pushing down here and mercury coming down here. And it turns out that the difference in height between the surface and the mercury is 76 centimeters, 760 millimeters, and we call that 1 atmosphere. The reason why we use mercury, which is a poisonous liquid in barometers, is because if we had to make a tube of water, given that water is much less dense than mercury, I think the density of mercury is 13.7 or something like that, maybe even 19.7. I get gold and mercury mixed up. 19.3. It's not 13.3. That the tube of water that could be held up by atmospheric pressure is 32 feet high. And so if we built a barometer, we'd have to have a hole in the ceiling. Or we'd have to have taller ceilings, otherwise the piece of glassware would break. Maybe you looked at this device last time, and we'll build one with glass when I get back. And we call it a manometer. Manometer, a manometer. There's a song like that. This device is used to measure the difference in pressure between atmospheric pressure and that of a gas in a vessel. Thus, this is an open manometer. There are two types of manometers, closed and open manometers. If there's an open manometer, the pressure in the atmosphere is pushing down on the open side, and then the other side is connected to a gas. Now the gas is clearly winning in pressure. Its pressure is more because it's pushing the mercury down. See, so this pressure is more. Let me write that here, little notes here. More pressure because it's pushing down, and this is less pressure. It's like the seesaw. Where's the fat kid? Here. This is winning. This is pushing down, and that's pushing down less. And so how much more? The difference in height is indicated by the amount of pressure difference. So you'd have to measure this height here, usually in millimeters or centimeters, and if the liquid is mercury, then you can, the pressure difference between the atmosphere and the enclosed gas would be measured in units of millimeters of mercury or torrs. Okay, so we talked about units of standard pressure, so I'm just going to blast through it. Well, when I refer to normal pressure, I should call it standard pressure. And we're also going to learn about a unit called standard temperature. Standard pressure are any of these measures that we see here, and also 14.7 pounds per square inch. Okay, now let's chat about Boyle's law. P1V1 equals P2V2. Sure is helpful if you learn it by name. All right, this is a classic Boyle's law graph. It's real helpful if you get the idea of the graph. That is, that as the pressure increases on a gas, the volume decreases. Let's see if I have the right slides here. All right, I'm going to pause and pull up something I want you to see. But then it won't seem like a long pause because it won't. I don't know where I am. Oh, you know what it is? When I leave the pin on there, it never operates. Sorry for that little brief delay. I figured out what I did wrong. Alright, so here I have a piston, and as you increase the amount of weights, and those are weights, the volume of the gas goes down, and as you decrease the amount of weights, the volume of the gas goes up. And they're inversely proportional. And this is animated Boyle's law, and you get the classic PV graph, which is, I'm going to probably need the help of a math expert here. It's not a, it's like a asymptote sort of deal. It's inversely proportional. And what would you call that shape? One of the things the chemist likes to do is to find the straight line. And the classic Boyle's law graph is volume versus pressure, and you get that inversely proportional graph. But if you do volume versus the inverse of pressure, then you get your straight line. And so there you have it. PV equals a constant is another way of suggesting Boyle's law. Okay, now Charles's law is volume over temperature, or V1 over T1 equals V2 over T2. Okay, T must be in Kelvin. And just to remind you, Kelvin equals Celsius plus 273. Now, if you add the 0.15, that's fine too, or if you just drop it, you'll get all your problems right. Of course, you still got 3 sig figs, and that's generally good enough. That 0.15 and worrying about it, you think it makes you all precise, but really what it does is it diverts you from making sure you got the right order of magnitude here. Now, we have a couple of labs to pick from here. One is finding absolute zero, and another is the lab you did last year, which was where you put the magnesium ribbon in, and you add the acid up here, and the acid made its way down here and made bubbles. And we'll make that decision in a day or two. We need to do, but we're going to do a real lab. There are a lot of cyber labs available with gas laws, and I may offer you the opportunity to do one to replace any lab grade that's not awesome. I was pretty harshing on you with the last labs because of poor work showing or whatever. Some of you got 8 out of 10s or 7 out of 10s, and I'm sure we can make that go away with a attempt at a cyber lab relating to one of the many opportunities to do so with gas laws. Okay, and then we get to Avogadro's laws, one of the ideas we learn about in the gas law chapter, and that is when you mix gases, if you have a gas that has a half a mole of pressure, a half a kilopascal of pressure, or a half an atmosphere of pressure, and you have another gas, their pressures simply add when you put them together. If you have a gas that has, if you keep them at constant pressure, then they add their volumes. The volumes add, the pressures add. That's what Avogadro's law is saying. Let me read it to you. The volume of a gas at constant temperature and pressure is directly proportional to the number of moles of the gas. So if you double the amount of moles, you double the volume, keeping all other things constant. And we get to the ideal gas equation. PV equals nRT. The trick here is to keep your R constant, 8.314 liters times kilopascals divided by mole Kelvin. If R is 0.0821, that's liters times atmospheres divided by mole times Kelvin. And you kind of got to use the right R for whatever the other units are in your problem. If your pressure's in kilopascals, you use this R. If your pressure's in atmospheres, use that R. There's another R if it's in millimeters of mercury, and it's we'll have to look it up, but I think it's 63.4, but I'm not going to write it until I'm sure. I'm going to pause because I can. Well, I found it on the internet, and it's 62.3 liters times millimeters of mercury divided by mole times Kelvin. Okay, so I have that. We can find that neater, or you can put it together neater. I think that would be helpful. This is a bit of a mess. Ah, look at that. There it is, all the different units of R. You don't have to know any of them, but I think your book only gives you this one. I mean, and the help sheets. But check your help sheets. 8.314. Now they call this joules per mole Kelvin, but it doesn't work so well with the ideal gas equation unless you think of it as liters times, what did I say it was, kilopascals divided by mole times Kelvin. That suggests that pressure, volume times a pressure equals work. See that? Because joules is energy, and that is and that is a very important thermodynamic notion that is true. You know, when you have liters times kilopascals, kPa, so a kilopascal is a Newton per meter squared, and volume is meter cubed. So when you cancel out the meter squared, we get mass meters times newtons, and that's like newtons is a force and meters is a distance, and joules equals force times distance. So that's just kind of an interesting notion to explain why this non-useful form of the equation is given. There's our famous PV equals nRT, which is being developed more, and the theoretical development of it isn't key, but there are two twists on PV equals nRT that you have to be able to handle. They're very important and they're not simple. One is when you substitute in for N moles, grams per molar mass. That's another labs we could do, because grams divided by molar mass equals that, and so instead of having 1, 2, 3, 4, 5 things, we come up with this equation: PV equals G over MM RT, and usually you have 5 and you search for the 6th in problems. And another thing that they like to do is pull density out of this equation. Density is what? Mass per, density is mass divided by volume, right? So I'm going to put G over V together, okay? So I'm going to put G over V together, and I'm going to put everything else on the other side. MM P over RT. So I'm going to rewrite that here. MM over RT equals density. And molar mass times pressure times R times temperature, always in Kelvin. Go Kelvin. Must be in Kelvin. Otherwise, you can't go if it's not in Kelvin. Kelvin was a very fast runner. All right, so those are two twists on gas law problems. I think that's enough for one day, and I would like you to spend the balance of your time, no wasted effort, no copying 21A off the back of the book. Get to work. I wish my period 1 class would get to work. They disappointed the sub yesterday, but whatever, we do the best we can here. So start your problem sets. I'll see you on Thursday. I may even see you for lab. I might be able to sneak in for lab, and we'll do the candy lab, and that'll be fun. I hope I can get there by 6th period or whatever. Good luck. Open up your books. Figure it out. You'll do fine. If not, I'll help you out tomorrow. Okay, bye.